Hey, this is Mr. James. In this video, we're going to be talking about area, volume, and similarity. First, a couple more conceptual questions. People are notoriously bad at predicting volume changes. For example, think about how long it would take you to fill up an Olympic-sized swimming pool with a regular kitchen faucet. How long do you think it would take? Well, you might think about a pool that you have at your house. Maybe it takes you a day or two to fill up that pool with a garden hose, right? So you might think, okay, if it takes me a day or two to fill up my pool, and an Olympic-sized pool is probably like 4 times as big, maybe it takes 4 times as long. But that's not true at all. To fill up an Olympic-sized swimming pool with a garden hose or kitchen faucet takes about 4 months. 4 months. Or counting the number of jelly beans in a jar, right? You might think that you could do this pretty easily, but in fact, most people count way, way too low. Or even the number of balloons you need to fill up your friend's car. Most people, if you ask them to go to the store and get some balloons to fill up someone's car, they'd get about 25 balloons. But in fact, it takes about 100 balloons to fill up a regular-sized car like this. So, why are we so bad at volume? Well, here's why. Think about the length of a line, the area of a square, and the volume of a cube. The length of this line is 1. The area of the square is 1 by 1, which is 1. And the area of this cube is going to be 1 by 1 by 1. Okay? Which means the volume is 1 by 1 by 1, which is 1. Okay? However, when we double the size of each figure, something strange happens. Okay? The length becomes 2. But now that this is 2 by 2, or 2 times 2, also called 2 squared, the area is now 4. What about volume? Well, it's now 2 by 2 by 2, which is 2 times 2 times 2 for the volume, or 2 cubed, which is now 8. So now, even though we just doubled the length of the sides, the area went up by 4, and the volume went up 8 times. Quite a lot. What about if we triple the sides? Well, again, the length just goes up to 3. That's what triple means. But for area, we now have a 3 by 3 square. That's 3 squared, or 9. What about for volume? For volume, we now have a 3 by 3 by 3 cube. 3 cubed is 27. So even though the length went up by a factor of 3, the volume went up by a factor of 27. Wow, that's a lot. So what does this all mean mathematically? Well, remember when we did similarity a few months ago? We would do things like A over B equals C over D. We would make ratios and compare the sides of two shapes. Well, we're going to do that here, except we're not going to just do it with lengths of shapes, like these are. We're going to do it with areas and volumes as well. Let me show you what I mean. If this length is A, this length is B, then the ratio of the length of the smaller figure to the larger figure is just A over B. It's anything for length. Length works that way. However, we just learned that area does not work that way. Area grows faster because it's squared. Remember in the last slide, okay, we saw that we have to square our numbers for area. Okay, so when we're comparing two shapes with their area, it'll be A squared over B squared. All right, gotta square those lengths to get the area. And what about volume? Well, volume we saw volume cubes, right? Volume cubes. 2 to the third, 3 to the third, everything to the third, right? So when we compare two solids, okay, and their volume, it's going to be the side length cubed over the side length cubed, okay? And let's scroll down to the bottom to actually show you what that means first. Each pair of figures is similar. Find the ratio of the perimeters and their areas. Well, in this first figure, we've got 2 hexagons, and the ratio of their sides, okay, is 3 to 9. Or you could write that again as 1 over 3 simplified. Okay? But what about their areas? Their areas is not 1 to 3. The area is you take the ratio of the side lengths and square the top and the bottom. So the ratio of the areas is 1 squared over 3 squared, which is 1 over 9. That means that this shape is 9 times the area of this first shape. Right? So the ratio of the areas is 1 to 9, even though the ratio of their side lengths is only 1 to 3. Let's check out this one, this next one. Pause the video here and see if you can write the ratio of their side lengths and the ratio of their areas. Alright, so here's how this would work. The ratio of their side lengths is just like normal. It's 6 to 4, or we've also written that as 3 to 2 if you'd like to simplify. On the other hand, the ratio of their areas is not 3 to 2, it's 3 squared to 2 squared, which means that that is 9 to 4, which is a much bigger difference than just 3 to 2. Volume is similar, right? I'm going to write down the ratio of their side lengths and then the ratio of their volumes, just like before. So, for this first one, these spheres, the ratio of their side lengths is 2 to 4 or 1 to 2, right? However, the ratio of their volume is very different. Remember, volume cubes. So it will now be 1 cubed to 2 cubed, which is going to be 1 to 8. So think about that. This sphere right here is 8 times the volume of the first one. 8 times, even though the radius is just doubled. If you'd like to, pause the video here and try finding the ratio of this next one. Alright, so the ratio of their sides is 3 to 5. Can't be reduced. But the ratio of their volumes is going to be 3 cubed over 5 cubed, because volume cubes, which means that this is 27 over 125. Look how big that got so fast. Right? The change in volume is quite big compared to the small change in side length. Take a look at questions 1 and 2 above. They're more conceptual questions. If we keep two figures proportional, but double the length of the side, so it seems like we're taking a shape and doubling the length of the side, multiplying it by 2, then all the other sides will also double. And the perimeter will also double. The reason is because anything to do with length, other sides, perimeter, anything to do with length will multiply by 2 to the first. Because length scales normally, right? If we're multiplying the length by 2, then all the other lengths will also multiply by 2. On the other hand, something that has to do with area doesn't multiply by 2, it multiplies by 2 squared. 2 squared. 2 squared is 4. So the area of that shape will quadruple. If we keep two solids proportional, but double the length of an edge, okay, so we've got now a solid, and we're doubling the length of an edge, multiplying it by 2, all the edges will also double. Again, they're still lengths. Okay, they're still lengths. However, the surface area will quadruple. It's an area. It'll go up by 2 squared. And this last one should say volume. The volume will multiply by 8 because it is now 2 cubed. Right? So the important thing to learn here is that length goes up normally. Area squares. Volume cubes. Now what does this actually mean for comparing two similar shapes? We'll flip to the back side and we'll talk about it. In these problems, it says the area of one figure is given. Find the area of the other figure. Okay, so we're comparing these two figures together here. Now normally, when we're doing anything with similarity, or ratios or proportions, you might think, okay, we'll start by comparing 4 to 9. So I'll write 4 over 9, and I'll set that equal to something. But that's not quite what we're going to do here, because this is the ratio of the side lengths. And here we're working with area. So we can't actually do that. We have to write the ratio of their areas. And like we said before, the ratio of the areas is 4 squared over 9 squared, which is going to be 16 over 81 equals, and they're giving me the area of the second one, but not the first, so call this x. The area of the first one is x. The area of the second one is 81. You can cross multiply, and it's pretty quick to see that x should be 16, just by cross multiplying like this. Okay. Now try pausing here and setting up this next one. Again, you might be tempted to write 4 over 6 as if we were comparing side lengths, but we're not. We're comparing areas here, right? So instead of writing 4 over 6, I will write 4 squared over 6 squared. 4 squared is 16. 6 squared is 36. And I'll compare that to the actual areas of the two shapes. The area of the first one is x. We don't know what it is. The area of the second one is 54. And if you cross multiply, you should get x equals 24. So the area of this shape is 24 centimeters squared. Scroll down to the last couple problems on this page. The directions here say the volume of one solid is given. Find the volume of the other solid. Now again, look here, we're talking about volume. So when we compare two side lengths, we're not just going to write 3 over 6. We're not going to write 3 squared over 6 squared. Since we're using volume, we're going to have to write 3 cubed over 6 cubed. 3 to the third over 6 to the third. So let's see. 3 to the third over 6 to the third. What's that going to be? Well, 3 times 3 times 3 is 27. And 6 times 6 times 6 is 216. Okay? And now I can actually compare the volumes. The first one is 512, and we do not know what the second one is. So to solve this, again, cross multiply. And you should get x equals 4,096. Look how big that is. The volume of this is 4,096 cubic yards. Right? Think about that. We only changed the area from 3 to 6. We changed the length from 3 to 6. We just doubled it. But the factor of the volume change is so big. That's why people are bad at estimating volume. Pause the video here, try and do the next one. In just a second, the answers will appear on the screen without any prompting, so make sure you try it before you go on. Alright, here are your answers. Remember, to get 729, I cubed 9, and to get 216, I cubed 6. Back up to those middle 4 problems. Alright, so for these problems, it asks me to find the missing length in each figure. Now let's think back. Length. Is length a normal ratio, a squared ratio, or a cubed ratio? That's right, length is a regular ratio. So when we see length, we can treat it just like we would any regular proportion or similarity problem like we did earlier in the year. Let's do the first one. It says this is 3, this is 6. So I'll compare 3 to 6. Okay. This is u, this is 4, equals u over 4. And if you cross multiply to solve, you should get u equals 2. Not too bad. Try the next one on your own. The work will appear in just a few seconds, so pause the video here. Alright, and there's the work. Remember, just setting up a ratio, a normal ratio, no squaring, no cubing, because I'm only working with length. Let's take a look at those last 2 problems just below this. The surface area of one solid is given. Find the surface area of the other solid. Well, look, I'm just working with surface area. And is it a regular ratio, is it a squared ratio, or a cubed ratio? Well, it turns out that area is a squared ratio. Doesn't matter whether it's surface area or any other kind of area. So when I write this, I'll have to write 6 squared over 9 squared. That comes out to be 36 over 81 equals x over 225. If you cross multiply, you should get the x equals 100. X equals 100. Pause the video here and try the last one. Again, the work will appear on the screen in just a few seconds, so make sure you do pause the video. And you should get x equals 144. At this point, please log on to IXL and try P11, T7, and T8. Good luck!